This is Faizan Kagri and welcome to our lecture series of Basic Mechanical Engineering. In our last session, we have seen what is heat energy, its sign convention, then temperature, then what is specific heat capacity, then what is enthalpy and internal energy. So in today's session, we are going to discuss comparison between heat transfer and work transfer, along with that thermodynamic laws. So let's begin with our first topic, that is comparison between heat transfer and work transfer. In that, first we are going to see similarities between heat energy and work energy. So the first point comes is that both heat transfer and work transfer are path function. So first of all, we need to understand that what is path function, and with respect to that, there is another term called a state function. So we would say that the property or a characteristic of a system which depends on a state of a system is called state function, whereas the one which depends on a path of a system, or we would say that the one which occurs during a process is called a path function. So for example, let's take a simple example, that ice. So we know ice has a solid state, right? At that particular solid state, the temperature of ice is 0 degrees Celsius. After some time, when we keep it in a surrounding, so it's going to melt. So the final state will be a liquid state. In a liquid state, its temperature is going to be increased. We would say it would be equal to the surrounding temperature. Let's say 25 degrees Celsius. So what happens? What has happened over here? So we would say that the temperature during both the states, the solid state and a liquid state, is different. In one case, it was 0 degrees Celsius. In another case, it was 25 degrees Celsius, which means we can say that the property, that is temperature, is depending on a state of a system. It varies as a state of a system varies. So likewise, we can say that pressure can also be different, then volume can also be different, that is pressure P1 at state 1, pressure P2 at state 2, similarly volume V1 at state 1, volume V2 at state 2, similarly randomness, that is entropy S1 at state 1, right? Initially solid state, so entropy will be nearly 0, whereas in a liquid state, the entropy has been increased, randomness has been increased. So what has happened? So we would say entropy is depending on a state of a system. That is, at one state it is S1, in another state it is S2. But this is not applicable on a heat transfer and a work transfer. Why? Because heat transfer occurs during a process, that is when a system undergoes from one state to another state. You can see on your screen, I have shown a closed piston cylinder arrangement. In that, in an initial state, you can see piston is in a downward position. I am supplying heat energy to a gas. Okay, so what is going to happen? So we would say initially at state 1, its pressure is going to increase. Okay, because of that, a gas is going to push a piston in a upward direction. Okay, so during from state 1 to state 2, there is a change called a process, and during this process, a heat transfer from a surrounding to a system has occurred. Okay, we cannot say that at state 1, Q1 is a heat transfer, because heat transfer is a quantity, or we would say that it occurs when a system performs a process. That is, when a system moves from one state to another state. Okay, we cannot say that at the final state 2, the heat transfer is Q. Okay, similarly, when a work transfer can occur, so we would say a work transfer can occur when a piston undergoes a displacement. That is, when there is a motion of a piston. Okay, that is, we know the formula of work. It is equal to force into displacement, and in terms of a closed system, it is equal to pressure into change in volume. So again, we would say that at state 1, there is no work transfer. We cannot say that W1 is a work transfer. Similarly, at state 2, we cannot say W2 is a work transfer. But what we can say, that a work transfer has been occurred when a piston has moved from its state 1 to state 2. That is a motion, that is a displacement is occurring. So whenever this displacement is occurring, then in that case we can say that a process is performed, right? And whenever a process is performed, a system follows certain path. So we can say that heat transfer and work transfer both depends on a path of a system, which indicates that it is a path function. Okay, so I hope you are clear with our first point, that is both heat transfer and work transfer are path function. Now coming to a second point, both are associated with a process. So it is very obvious that during a process, this heat transfer and work transfer happens, that is, it is depending on a process and not on a state. Okay, now third point indicates that both are inexact differentials. Now what does inexact differentials? So we would say that inexact differentials are represented by partial derivative, that is called del. That is a one whose complete differentiation is not possible. So over here you can see I have indicated by integration state 1 to state 2 by del q, that is heat transfer is represented by del and not d. Whenever d is used indicating exact differential, but when a del is used, then it indicates partial derivative. We would say it is not possible to integrate heat transfer in a limit from state 1 to state 2. So I have given an example that I cannot write integration state 1 to state 2 del q is equal to q2 minus q1, which is not possible. q2 minus q1 indicates what? That we have q2 heat transfer at state 2 and q1 heat transfer at state 1. But now I need to determine that how much heat energy has been given to a system, right? I need to find out a total heat transfer. So what I can do? So I am going to convert this heat transfer in a terms of exact form. That is, we know the formula of heat transfer in which the property depends on a state. For example, Q is equal to mc delta T. So in that delta T, there is a change in temperature. So we would say the temperature is depending on a state, which means we can do a integration as well as a differentiation of this temperature term, that is depending on a state. So I have written integration from state 1 to state 2 mc dt. Now dt is an exact differential, that is, we know T2 is a temperature at state 2, T1 is a temperature at state 1. So we can write integration state 1 to state 2 del Q is equal to mc T2 minus T1. Similarly, work transfer is not depending on a state. So we cannot write that integration state 1 to state 2 del W is equal to W2 minus W1. Okay. So how we can write? So we know the formula of work transfer. W is equal to P dV, that is pressure into change in volume. So I have written it is equal to integration state 1 to state 2 P dV, where dV is a change in volume. So we would say that volume is a state function. At state 2 we have volume V2. At state 1 we have volume V1. So we can determine the total work done by a system by using this formula. So I have finally written answer is equal to P V2 minus V1. So both are inexact differential. Every time we are going to represent Q and W by a partial derivative, that is called a del. Okay, del Q and del W. We are never going to write it as dQ and dW. You have to keep this in mind. Okay, now next point is both are boundary phenomena, that is heat transfer and work transfer are boundary phenomena. So what does this indicate? What does this mean? So we would say that heat transfer occurs across a system boundary. You can see on your screen that a heat energy is given which crosses the cylinder boundary and enters into a cylinder and hitting the gas, which means a heat transfer is a boundary phenomena which crosses the boundary, which occurs across a system boundary. Similarly, work transfer. So we would say during a work transfer, piston is moving, right? Piston is going to move from downward side to upward side, which indicates what? The boundary of a system is going to change, which is occurring across a system boundary. So these are the similarities between heat transfer and work transfer. Now let's see the dissimilarities between heat transfer and work transfer. So the first dissimilarity is heat energy is considered as a low grade energy, whereas work energy or work transfer is considered as a high grade energy. So taking a simple case of a IC engine, which we have already seen in our last session, that in a IC engine, air and petrol mixture enters the system, it generates a mechanical power by combustion, and after that the exhaust gases were leaving the cylinder through the exhaust valve through a silencer, right? So that exhaust gases which were living were possessing heat energy. Okay, which indicates what? That heat energy is not completely converted into mechanical power. Only certain portion of energy is converted, which indicates that heat energy is which type of energy? That is a low grade energy. Whereas the mechanical power or a work energy is always the greater, or we would say it is always considered as a high grade energy. Now seeing the next point, we know heat transfer occurs because of what reason? So we would say because of a temperature difference between the two bodies. That is, one body will get a higher temperature and another body will get a lower temperature, right? Whereas work transfer occurs when a body undergoes a displacement or a body is moved from one position to another position. Okay, so you have to keep this in mind. The second difference is heat transfer occurs because of temperature difference, whereas work transfer occurs when there is a displacement. Okay, third point, heat supplied. So now this point is based on sign convention. Okay, so heat supplied or absorbed by the system is considered positive, which means that a system or a gas has obtained energy, has gained energy. So something, when it is added to the system, then it is considered positive. That is, energy is added to the system, heat energy is given to a system. Whereas when a work is done on the system or a work is supplied to the system, then it is considered negative. Now what does this indicate? So it indicates work done on the system. I have utilized my energy in order to perform a work on a system. Okay, so that with respect to us is considered negative. Okay, next point, work has a ordered motion, whereas heat has a disordered or a random motion. So we know that when a push is given to any object or a body, then it is going to move in a direction of a force, right? That is a fixed direction wherever a force is applied. Whereas heat energy, or we could say whenever the heat is given to a gas, then a molecules have a disordered motion. That is, it is going to move from one place to another place. Its motion is not fixed, which indicates a random motion. Okay, so these are the most important points indicating the dissimilarities between heat transfer and work transfer. So now let's begin with our next topic, that is thermodynamic laws. So the thermodynamic laws which we are going to study are Zeroth Law, first law and second law. So now let's begin with Zeroth Law of thermodynamics. So what does Zeroth Law indicates? So it indicates that, as you can see on your screen, I have shown three bodies, body A, body B and body C. So let's say that when the two bodies B and C are in thermal equilibrium with the third body A separately, or we can say that body A and body B has the same temperature. Similarly, body C and body A has the same temperature. Then what we can conclude? Then we can conclude that body B and C also have a same temperature. That is indicated by Zeroth Law. So as you can see the statement that when the two bodies B and C are in thermal equilibrium with the third body A separately, this term separately is most important. Okay, and the two bodies B and C are also in thermal equilibrium with each other by Zeroth Law. So this law is a principle of temperature measurement. This law is used to determine the temperature of a system. This is an application of this Zeroth Law. So on your screen you can see that I have shown three objects. So object 1 is my thermometer, object 2 is my, let's say, some system, and object 3. So thermometer is going to measure a temperature of object 2, okay, separately. Similarly, it is going to measure the temperature of object 3 separately. So if temperature of both this object 2 and object 3 are same, represented by a thermometer, then we can say that object 2 and object 3 have a same temperature or are in thermal equilibrium without actually bringing these two objects, object 2 and object 3, in contact with each other. So we can say that an application of Zeroth Law is that it permits to predict the equality in temperature of our two bodies without actually bringing them in a physical or a thermal contact. Okay friends, so I hope that you are all clear with Zeroth Law of thermodynamics. So today we are keeping up till here. In our next session we will continue with our topic of first law of thermodynamics, its applications, limitations of first law, and then why second law of thermodynamics have come in picture. Till then, stay tuned. Thank you.